So, hello everybody, and welcome back to another Thursday at BrIAS Seminar event. Also, today we will have two seminars like all other Thursday. So, in case you have doubts on when we are going to have seminars, it's on Thursdays. And so, today we will go more on, we will have a first talk more about networks and how to virtualize them, and we will have a second talk more on the robotic side. But I want to introduce our first speaker, that is one of our senior fellows here at BrIAS, is Giang from the University of Dresden. And I am pretty sure that yesterday we spent a long time speaking together about his research subject, which I find very interesting because it touches how the network influences reality and influences the need for specific performance for control. So I am leaving him the stage. So please, Giang, the stage is yours.
So good afternoon, everyone. So first of all, thank you very much, Emmanuel, for the very kind introduction. I'm Giang Nguyen, and if you, from my last name, if somehow you guess that I'm from Vietnam, you are 100% correct. And I have been living in Germany over the last almost 15 years, from doing PhD, postdoc, being a founder of a startup. And currently, I'm assistant professor at the Technical University of Dresden. And today, I would like to contribute the talk about softwarized networks. So not okay. So particularly the software aspect of communication networks, and so the goal is that we exchange the ideas, and hopefully we can find like interesting synergies, how the software networks can contribute and also can learn from robotics, AI, and automations. So first of all, let's have a look at the current status of the network, the largest network in the world, which is the internet. So with the internet, currently we have no any problems sharing information, ideas, video, audio across the globe at any time. So it is a democratizing the access of the information. However, from our viewpoint, the internet would need to evolve into the next generation, which is a tactile internet that can democratize the access not only to the information, but also to the skills and the expertise, where the human can learn from the robots, and the robot can also learn skills from humans. And in order to do so, we would need the sense of touch. And when we look at the current status of the internet, it cannot fulfill the requirements of conveying the sense of touch from one point to another, mainly due to the large latency. And therefore, our approach is to softwareize the networks in such a way that it should be programmable and subsequently will be flexible. But at the same time, the flexibility will also allow for to speed up the network and also to make it more resilient to eruptions. All right. So how we see the networks and how we see the interaction between the human and the machine. So first of all, I think until now, probably we have a common belief that at some point we will have completely autonomous systems with the help of automation, AI, robots, so that the human might be at some point, we just need to sit down and then let the robot do the job. But until then, there might be some transition. So the robot and the human will need to collaborate and to learn from each other. And even with completely autonomous systems, robots and humans still interact. And currently, the interaction will need a communication network in the middle. So what is the challenge in this scenario? So first of all, the challenge coming from the human side. So we humans, we are very sensitive and will be affected by the latency. So in this case, the human with the virtual reality glass will try to catch the ball in the real time, right? However, by the time that the human realized that he or she can catch the ball, it was already too late, right? Simply because of the whole conversion of the signal from the real world to the virtual world, and so on. And needless to say about the sensitivity of the human brain, different genders, or different in the expertise, or maybe different in the ages. And at the same time, machines are also are affected by the delay. So until now, I think with the control community, we are pretty understood that we are pretty certain that the networks with the loss, latency, and particularly the jitter are not reliable enough to decoupling the control far away from the system, in this case, the robot. And if we have the large delay with the closed loop control, then the system at some point will become unstable or maybe even dangerous when interacting with the human because it cannot control the behavior anymore. And why it is the case? We thought that, okay, the network just deliver the service. So nowadays, if we have the service we would like to use mainly with the cloud service provider, then there are some connection with switches and routers. There shouldn't be any problem. The reality is, in the middle, there are a bunch of network functions that we are not very visible to the end users. They are firewalls, WAN accelerators, cache, and also like for security, we would need intrusion detection and so on. So all those network devices, they are specialized box in hardware to try to optimize for the performance. And there are not a few of them. And actually, there are many of those in a typical network. And all of those, they contribute to the complexity of the network and also eventually to the flexibility and the latency of the network. So what a softwarized network would look like. So if we would go from the current state of the network with dedicated hardware, then each of the network functions, for example, firewall, intrusion detection system, IDS, or maybe one optimizer, each of them running on a dedicated hardware with operating system, and then with the algorithm on top. Even within, if those network functions or devices coming from the same vendors, there are already complications when configuring them manually and connecting them physically. And imagine if each of those network functions coming from a different vendors, right? Slightly different interfaces, slightly different commands, and so on. So the management of those networks will become very complicated. And therefore, with a softwarized network, there will be a transformation from dedicated hardware using now commodity hardware. Typical switches or routers that we can buy over the market, typical servers, so that we can run virtual machines, or maybe Docker container. And on top of that, we can implement those network functions like firewall, intrusion detection, or maybe one optimizer completely in software. And then what is the benefit? Those functions will become like going to a supermarket. Depending on our need, we will select some of those and then connect them in software completely. In this case, we would need only 2 network functions, but we can also select 3, 4, 5 network functions on our need. And what is the benefit of this? So the first benefit is the reduce of latency. How can that be possible? So let's have a look at the current state of the art when we deploy a service between the human and the robot. For the service nowadays, typically we would need cloud service provider like Amazon or maybe Microsoft Azure and so on. And then we deploy the service there, having a connection from both sides, human and robot, to the cloud. And then somehow they should communicate and interact. With this case, the data have to travel from the human to the cloud, maybe 100 kilometers away, and then back to the robot. So the round trip time could be 50 or maybe 100 of milliseconds, simply because the information has to travel for a long distance. And since we have a physical distance between the two entities, and we are limited by the speed of light, so there are some fundamental limits that we cannot exceed in this case. However, with the softwarized networks and the flexibilities, we can potentially change the transmission of information between the two endpoints. And in this case, the human and the robot can be connected using a completely shorter distance. And the service will be deployed at a very close distance to either the robot or the human or both. And we call this paradigm mobile edge computing. So we leverage the computing capabilities inside the network to implement network functions. Another advantage of this paradigm, once we have the infrastructure of the mobile edge computing, then in principle, we are able, and we should be able, to implement and deploy new network functions, or maybe new applications in the network, so that we can leverage the low latency, since now they will be in software. Okay, so I hope that until now I motivated us sufficiently so that I can move to the 3 highlights of my work that I would like to share with you today. So in the first line, the first contribution is to tackle the computing latency in softwarized network. The second is about audio processing, so mainly how we can leverage the softwarized infrastructure of the network to do something else, so new applications. And the last highlight will be about the resilience, since we have the software, not the dedicated hardware anymore, and the software will share the same infrastructure that they might need to compete with the resources with one another. So resilience could be a concern. Okay, so now I will jump right into the first work, trying to reduce the computing latency. But first of all, let's have a look at the scenario that we have. So the block on the left-hand side is the building blocks coming from the sensors to the mobile communication system, and then going back to the mobile communication system, and then to the actuator. The block on the right-hand side is the mobile edge computing server. Okay. So research have been shown that in order to have the real-time, perceived real-time interaction between the human and the robot, in this case teleoperation for example, then we would need to fulfill 1 millisecond round-trip time. For audio and video, normally we can tolerate higher latency. For audio, for example, up to 5-10 milliseconds. Otherwise, might hear the echo and so on. For video, we can tolerate even larger latency, up to 30 milliseconds. But now, with the sense of touch, we have only the delay budget of 1 millisecond. And if we have to deduct the delay from other components, like sensor, actuator, and so on, then we have only roughly a third of a millisecond for the computing. And we already did a measurement study, and it turns out that by no surprise, we cannot meet that delay. Okay, so now we would like to pinpoint, so what is the bottleneck, and how can we do with it? When we look at this from between the two PC or maybe two servers with exchanging the information between the two virtual machines, then the information will have, or the data will need to travel over many components. And many of those, for example, with the bridge, the physical network, and so on, we consider them as state-of-the-art, and we will take them as they are because we have less influence on how the device will be manufactured. We have less influence on the vendors or maybe the operators. However, what we can have the influence is how we implement our network function inside the virtual machine. This is, maybe we can have a novel approach for doing this that can help us to reduce the latency. We will go one step deeper and see what is inside the virtual machine that can potentially hinder us from achieving the goal. And then we found out two observations. But first of all, inside the virtual machine, or if we build like an application currently, and particularly the application that need to exchange information with the outside world, we would need CPU, of course, as always, but also inside the operating system, we would need the kernel space and also the user space, where the new network function will be implemented inside the user space, and the networking functionalities mainly reside in the kernel space because they need to be optimized. They also need to be pretty small. Okay, and then there is two bottlenecks. The first one is the CPU. Every time there is a new packet come into the system, there will be interrupt. And then the CPU, whatever it is doing now, it has to push into the cache, take the new data, trying to do it very quickly, complete, and then resume with the work that it has done before. And if there are so many packets coming in, and the CPU cannot keep up with the rate, and then we have interrupt all the time. And eventually, the context switching between computing and storing, caching, and so on, it will decrease the overall performance of the system. The second bottleneck is the read-write operation of the data when there are data passing between the user space and the kernel space. And the reason is that all the network functions, they have to pass through the network functionalities in the kernel space. So always exchange of data. And every time there is a copy read-write operation, there are overhead. And our approach is that, okay, we need to remove those bottlenecks. we would like to eliminate completely the context switching. And then we have a look into the set of network functions that we implement and then we deploy, and see which one should be feasible to be implemented in the kernel space and then stay there for the whole time, and which network function should be or must be implemented in the user space. For example, due to the availability of the library. Nowadays, if we program, we have to use library. We cannot program from scratch. Okay, so these are the category, but of course we would need some trade-off, or maybe some, for example, we would need to trade the storage, in this case, the resource that we provide for each network function, not sharing one virtual machine anymore, but each one will have its own virtual machine. Okay, and we call our strategy like Canvin. Now, if we look at the strategy, after we change it, so we have completely different virtual machine, A, B, and C. They are in the data plane, okay? And some network function, in this case, basic network function 1, will stay completely inside kernel space. Okay. And then once the data was processed inside this network function, it will go out and never go back to the kernel space again. And then the data will be subsequently be processed inside another function 2 or 3. And they are more advanced, so more complex, and they would need to be implemented inside the user space. What do we achieve with this strategy? Let's have a look at this plot. So on the x-axis, we have the round trip time. And the y-axis, we have more or less the distribution. Now, we notice the black line is the threshold, a third of a millisecond we would like to achieve, while the other line at the very right-hand side, they are the state-of-the-art, which is the centralized approach, sharing virtual machine and then sharing the CPU, context switching, and so on. And I think it is pretty obvious from the graph that the state-of-the-art rarely or barely meet the requirement of the latency. On the other hand, our approach, Canvin, depending on the packet size, we can move the line way behind the threshold, so meaning that it can meet the threshold most of the time. But how far can we move the line to the left-hand side? So there is a physical bound limitation, which is the lower bound of the latency that we can achieve when we do nothing. Data coming in, going out immediately. And in this case, so our conclusion in this case is that whatever the technology provided us, there will be like 10 times increase of the latency in the state-of-the-art. However, we can reduce the latency significantly close to the lower bound. And if the technology advances regarding the hardware, operating system, and so on, we can always move and follow the lower bound. All right, but there must be a trade-off. And in this case, we see that we have very little room for more advancement. Right? And the second disadvantage is that we have to sacrifice in the bandwidth. We cannot process very quickly. And therefore, in the subsequent study, what we would like to learn is to see how we can apply this current framework to process the data, maybe for a different kind of application that doesn't really need extremely low latency, but have a requirement for more bandwidth. And in this case, we selected audio. I mean, we could jump directly to video, but maybe step by step. So this is how our approach. From haptic, we go to audio. So, and the application in this case is audio processing. So in factories, surprisingly, audio is a very common practice to monitor how the machine works. One of the reasons is that with the video, we always have to handle the obstacles. Right? With the audio, we don't have such a problem. We can deploy microphones in many places. And from the experience of in the factories, we learn from the people working in the factories that normally a malfunctioning machine will cause a very strange noise that happen way before something really happening that the camera can observe. Okay, but then the challenge here is that microphones, they collect everything. All the audios they collect, and therefore the audio from one machine will interfere or maybe will be combined with the audio from other machines. Luckily enough, this problem has already been addressed by a setup or family of algorithms, which is a blind source separation. So by using such algorithm, one can restore a rough estimation of the original audio sources. Here, so we have some formulas, but basically what we collect at the end is a set of mixed data, and we need to apply blind source separation algorithms to separate them. In a common approach, we would like to send the data, so collect the data, send them over the internet to a cloud provider. And then because the computing resources over there is abundant, and therefore it would help us to separate the data and have the result very quickly. However, if we do so, we need to pay two things. A large amount of data coming to the cloud provider, we have to pay one time. And if the computation is complex, the calculation will take a long time, we need to pay also for the computing. And it is not very cheap. This is how the cloud provider, they make the earning. And therefore, what if we can do two things? We distribute the computation over the network devices in the middle, along the path, so that the data will be pre-processed somehow. And hopefully that at the end, the pre-processing will significantly reduce the computing load at the cloud provider. And also, we also hope that the data that we send over the path can be reduced, so that eventually when the data coming out of the local site to the cloud, it was reduced. So we don't need to pay too much for the data transfer and don't need to pay too much for the computing. But then we have two challenges. The first one is the current blind source separation algorithm is centralized. But now if we want to distribute the computing load to a sequence of network nodes, we need to transform such algorithm from centralized to decentralized. And the second challenge is the current networking is designed for send and then transfer. So it doesn't want to store the information. So as soon as the network device would receive the data, it will try to send out as quickly as possible because this is the job that it should do. Now we try to tweak it a little bit so that not only it is receiving and sending the data, but also try to compute a little bit, but without causing too much delay. So first thing first, we look at how we can transform the algorithm. And then we look at the algorithm can basically be divided into 3 building blocks. So data extraction, data estimation, so doing like in several rounds until it can really estimate the original data, and then finally to collect and recover the data. Okay, now and therefore we will do the separations and data extraction and data estimation repeatedly on the network devices along the path. And at the end, because the data recovery will only be done once, we will keep it at the end server. Then, of course, we have different strategy. Either we try to compute as much as possible at the early network nodes, or maybe we try to somehow balance the load between the network nodes. Okay, 2 strategies. Now coming to the second challenge about networking. So, as I said before, if we rely on the current network, data coming in, compute, data coming out, then we have like a stop and go, which is very slow. If we transfer the data for the computing, and then we look into the data, then probably we already violate the one of the principle of networking, which is end-to-end. So we should not change the data at the intermediate nodes. And therefore, our approach is we need to introduce one additional module doing the 2 things. One is that it should have the memory to look at the data and then to decide whether this kind of data should be forward right away or maybe should be processed. All right. So quickly about the results. So the yellow line is the state of the art, or maybe this is how we would like to compare against. And every subsequent line will represent the number of network nodes that we introduce between the sender and the receiver. So could be 1, 3, 4, 5, 7, and so on. And then we observe that the more network nodes in the middle that we have, we can reduce the delay, the overall delay of the data processing, so up to a third. And the interesting thing is that if even we introduce or we pre-process the data with 1 or 2 nodes, the gain is already pretty significant. And also confirming to our observation, so the residual computing load at the subsequent node will be reduced. All right. So now we also learned that with the Softwarized network, for certain applications that doesn't need very super low latency, but with the requirement for high bandwidth, and depending on our design, we gain something. The third contribution that maybe I will go pretty quickly over is about the resilience. So how the software implementation of the network function or new applications can or should be designed, and the network, how it should support this kind of application design to improve the resilience. So it means that if the function failed, then the backup should be up and running as quickly as possible. Or the best thing is there is no disruption, no interruption between the two events, failing and resuming. And currently with the cloud computing, there are practices which is already there in cloud computing. So doing the migration of the whole virtual machine, or maybe more lightweight, is to migrate only the application part, right, using, for example, Docker container. We ask ourselves, can we do even better? So not the interruption time, not only in the order of seconds or tens of milliseconds, but already maybe a few milliseconds. And therefore, we came up with a scheme which is a state design. By state, we define it as intermediate results of a computing of a certain function. And for that, we divide the state into two parts. The part that doesn't change very often or optimally doesn't change at all. For example, if we consider IP address, port number, and so on, they rarely change for one client. But the other type of state is the temporary, the temporary result of the computing that change very often. When we look at the design in the state of the art, there are basically two approaches. The one is using like very reactive, right? So when we decide that we would need to replicate a certain application, then we transfer the state. The new application is up and running, and then we remove the old one. This is a very reactive. However, in reality, there are events that we cannot be react. If we react, might be too late. For example, failure. If an existing application fails, it will not respond. It will not be there and to transfer the state. And therefore, another approach is to be very proactive, sending the data, updating all the time, with the drawback that both instances of the application have to be up and running, or maybe we have to store the state into external database, which reduce the performance. And then we came up with our own approach, and we call it StateOS, because it is basically provide application on top, so it provides an abstraction layer for application to build their application that can support the scalability, fault tolerance, and also acceleration. And it supports both strategies, reactive and proactive. All right, so we measure whether this StateOS can really help in increasing the resilience of the system by looking at the time needed to copy the state and then transfer it from one place to another. And depending on the number of flows, which represent the workload in the system, the saving can be up to 60–70%. All right, so to sum up with the highlights that I have already presented, first of all, we tackle the challenge of reducing computing latency inside softwarized networks. We came up with a solution, Canvin. Second, we would like to see whether the softwarized infrastructures or the networks can be used or leveraged to do something else, maybe with higher latency but larger bandwidth. And in this case, we came up with fast ICA, which is the independent component analysis for audio processing. And the last contribution that I presented today was about StateOS, which tried to address or improve the resilience of virtualized networks. And the approach that we did was pretty pragmatic, as you observe. We try to find out what is going on and then try to make it better. And the overall theme of research group, the research of my group is try to collaborate. And in order to collaborate, we are willing to go extra miles, not only to focus and stay within our circles of networking, but also try to learn new application, new domain. Like in this case, we try to learn audio processing, or maybe we try to learn into the kernel space and so on. All right, and the work that I have presented it's not that I could do alone, but it is a whole group of the team that have been working with me over the past 3, 4, 5 years. Now, looking forward, how the Softwarized network would contribute to robotics, AI automations. So first of all, I would like to sketch a few ideas. So first of all, after the discussion with Emmanuel, maybe the network can also will be a reliable channel to provide the reference for traditional control systems. Right? However, what I'm also interested in is to apply or to adopt some of the control theory into the networking part, because in the networking, we need to control something. For example, the flow controls, or maybe the congestion control. And maybe some control framework, like explicit reference governors, with the advantages of low computation costs compared to like optimization of the constraint control, that might be beneficial for the networking part, where we need to deliver things pretty quickly. And at the same time, so in parallel to the academic perspective, I also would like to contribute into the domain of robotics, which could also have the impact in the society in a very direct way. In this case, I'm in the collaboration with BRAM, and the application that we would like that we find the synergy is the set of robots that collaborate with one another. They are specialized robots. Each of those will be very good in certain things. Some will be static or stationary, others will be mobile. And they collaborate to achieve a common goal. And since they need to collaborate, they need to share information. And in this case, the sensors from the robots will be collected over the network to a centralized server for the aggregation to understand the environment, and from there, one direct application is to guarantee safety, avoid collision, and so on. And currently, we came up with a framework which is flexible, based on software that components inside each entities can be deployed using Docker container, and then depending on whether the delay budget, the CPU budget, we can decide whether we would like to prioritize for compression. If currently the data will be huge, then we need to compress before we send out. Or if we can relax on such constraint, then maybe we send the data right away. All right, so I hope that this is simply the starting point of the discussion, and I'm also open to other discussion and your ideas. And first of all, I think regarding robotics, maybe in a few minutes, Bram will tell you way better than I did. So, but anyway, questions are welcome.
So, are there questions from the public?
Please. Okay, Bob.
Thank you. Thank you. How you would you also, so the one thing is also the hardware, and how your research can influence the developments of the hardware for better communication. Because now you said you use components available, but I don't think robotics is yet so powerful. But imagine in the future that we really can dedicate, make the communication devices that, focus on the needs of robots.
Okay. So regarding, I think it makes a lot of sense. So we try to, so one of the goals, so maybe I need to take a few steps back to answer the questions. So one of the goals of transforming the network functions or the network architecture from dedicated hardware to software is that we can simplify it. And once we can simplify it, we can really narrow it to a particular application. Depending on what are the functionality that we need, we will tailor it. Now coming to the hardware. So currently our approach is to take whatever available in the market. However, I hope that by simplifying the software to certain level, we realize that this is a set of functionality which is simple enough that can be implemented in the hardware. Nowadays, there are also hardware that allows for programming and reprogramming, and maybe that will be like the platform for implementing the innovation inside the network that will be optimized for a particular application.
Yeah, because I think now communication devices are mainly for mobile phones and computers with those requirements, but not including what we need from robotics. So we need to adapt to what is available. And of course, I think we need to the opposite. And another aspect is, one thing is about communication, but what about also indoor localization and positioning? Because there are a lot of signals between the different agents. I will explain a bit more, but we use ultra-wideband localization. But it can also be a 5G network and so on, but also there we see that the devices are not made sometimes to make that possible. And also maybe there we can combine communication with also relative pose estimation and indoor GPS system.
Yeah. So before addressing the second questions, I would like to comment on the last part that you said. This is also the purpose of joining as a fellow of BrIAS is also to work with other teams, for example, robotics, to learn what is the current limitation of the network to support a certain domain, and we would like to learn from it. To see what are the aspects that the network can do better. Because from our own experience, when we approach those things, those challenges, like in audio, then by digging deep into such a domain and learn from those, we found some solution. Maybe not the best one, but one step better than the previous solution. And regarding the second question about sensing, I think it is a super interesting domain. And in particularly in the next generation of mobile communication system like 6G, there is initiative to combine communication and sensing together, so that we don't really need two systems, but simply using, so using the mobile network, the signal, and then to use it for the sensing at the same time. But also to combine the mobile communication networks with other technologies like ultra-wideband and so on. Because for ultra-wideband, compared to the cameras, it has a huge advantage in privacy, for example, privacy protection. So I think it is, unfortunately, I don't have any answer for such a huge problem, but I think there are some direction that we can explore. Thank you.
Other questions? A little bit shy today, but well, I might have a few. As you know, I worked in a similar problem from the other side, so from the side of control at the beginning of my career. And I remember already 20 years ago in a plenary talk by Andrea Goldsmith in one of our major conference that she was presenting us the need to think about co-design between control and communication. So this is something that I've heard in multiple conferences, and then somehow it always remained, at least in our community, a niche. What happened in yours? Now I'm curious.
I think it is the right time. I think even though the topic was research 5 years, maybe 10 years ago, but I think this is the right time because we also receive the demand from actually industry. They are also interested in control and communication co-design. I'm not quite sure what is the motivation behind the industry, I don't know, but we receive the question from industry that they are also interested in this topic. So if there is a chance that maybe we can explore more about this, then of course I'm very keen on.
Another question that is kind of associated, that is, it's always, we often see trying to do control, try to do robotics, using existing network, using existing protocols. The real question is, aren't the need of, so the need of the current internet is to transmit data, to transmit videos, to transmit this kind of stuff. It's not about real time, it's about bandwidth, it's not about latency. So a question is if it's the right path to follow, or if we should think for this future application more of a different topology, more of a different way in which the network manages the packets, with much more close to the physical layer rather than too many abstraction layer. I don't know how you see it.
Yeah. Okay. So I have to admit that so this is often the case that when we have there is a collaboration between the control and the communication communities. Eventually, the control community have to assume that the network is unreliable. I think this is true, but also sad. And currently, the networking community, we are trying to improve it, right, to increase the reliability of the network, reduce the latency, trying to have not only the long tail of the latency, but maybe more skill to a certain degree. This is a work in progress. However, there are some initiative, particularly it is time-sensitive networking, which is like the idea in local area network and in the industry. And now would like to more or less employ the same idea with the synchronization of the clock between the stations and the receiver, sender receiver and so on, so that they can really schedule when to send a packet, when to receive the packet. Normally, for networks like Wi-Fi, that we don't have any dedicated frequency. It is shared frequency. Anyone can access, can sense Wi-Fi. I think it might be challenging. However, for dedicated bandwidth, like in mobile communication system, then nowadays with campus networks, for example, that one can have the full control from the core network to the RAN, and then with the frequency, dedicated frequency, I think we have some hope that we can really have the control over the behavior of the devices inside the network. Oh, okay. Sorry.
I don't know if this makes any sense, but for this very specific types of communication, like you're controlling a physical device, is there any way to have predictive communication? So in the video that he showed, it seemed that there was trembling because the moment that the thing was going down, they were going up, but you can predict that the movement is going to go a little bit in that direction, particularly if the device in the sender has a camera or something that is very specific to the application. I don't know if that can be done or has already been done.
Yeah, so I think it makes complete sense. So as a matter of fact, also we did in SETI the work with anticipation. So the motion of the hand when we try to grab something, so normally we can detect this even up to almost 1 second before we grab the object. So we can anticipate it. And it is also our long-term goal that we use the gain in the latency to inform the network and then to better schedule or maybe better optimize network resources to avoid collision and so on. So I think it makes total sense. Thank you.
Well, I will close. Oh, there is a question, so I will not close.
I have a question about the robots that are being used in surgeries. They use 5G networks. How dangerous it can be with this problem of latency?
So the latency, the challenge of latency in remote surgeries. Yeah. So we, it is a real challenge we address in SETI. So SETI is a whole research cluster consisting of almost more than 30 professors and more than 70 PhD students, postdoc, and so on. And this is one of the scenarios that SETI tried to address. So in phase 1, we address this as a training for surgery. So we try to, because really to guarantee low latency, reliability for the wireless network, for such application with stringent demand, strict demand like surgery, it is really a challenge. But in SETI, what we try is to meet the demand for training of surgical person. And in the next phase, we will try to address this. But this is ongoing work, and this is really a challenge.
Okay, so I will conclude just with a small observation question, more or less. That is, when I was making you the question about co-design, of course, answered for the side of telecommunication. I must say that as a control guy, although we have spoken about this co-design for a long time, still it is very rare that in a real implementation we implement the state of the network as one of our control variable, while instead it's very important because if I know that the network is poor, I know that I don't have to do aggressive maneuvering and vice versa. So there is a link there. And somehow also I'm looking at Bram because together we are some of the men responsible of the course of robotics. This is aspect that, for instance, we never expose our students to. Instead, it's something that it's absolutely relevant. I don't know how you see it.
It's really a challenge, and I'm excited to to address this jointly.
Okay. So with this. I go in the camera field. So with this, I want to thank once more Giang for the very interesting presentation. And as usual, I invite you for our coffee break, and then we will have a second very interesting talk by Bram. So see you in 10-ish minutes. So, welcome back for this second seminar of this Thursday. It is really with pleasure that I introduce the next speaker. So, the next speaker is Bram van der Boer. I hope I pronounced it decently. So, I'm very happy to introduce him because he's a very important and special person for the BrIAS, as he served with me last year as the program director on the team of robotics. And furthermore, Bram is also one of the most known and relevant roboticists we have for sure in Belgium, but I would say also in Europe, and is active in a number of very interesting fields, very often in close contact on trying to do something that is for the common good. So I'm very, very pleased to introduce him, and I leave him the stage.
So thank you. So my presentation will be about core robotic technologies for sustainable robotic startups, because it's about sustainability. So we see, of course, robots playing an important role to improve the digital transformation, so improving productivity, return on investments, and so on. So typically what companies desire. But on the other hand, you have also the sustainability transition we need to make. And sustainability we not only see on economical side, but also on societal side and on environmental aspect. And this is, of course, typically more what the society or the government enforces. Think about, for example, the EU Green Deal. And in robotics, in our research group, we want to combine the two, of course, in a robotic context. And so making both groundbreaking new novelties, but gradually improving it and increasing the TRL in order to support existing companies in robotics. But yeah, we don't have so many robotics companies in Belgium or Europe. So that's why we're also trying to make startup companies. And of course, the robot is an integration of very advanced technologies, core robotic technologies, and they provide capabilities. And it's about sensing, processing, and activation. And on the other side, you have the robot applications. And because, for example, for a drone, the sensors were small enough, the battery density, energy density was good enough, the motor strong enough, the processing small enough and powerful enough, literally a drone could take off, and you see the enormous amount of applications of drones, for example. But of course, collaborating drones like here Brian did, and having manipulators on drones is still a challenge. But also reinforcement learning, how to see, but also touch and so on, and the work of Kelly on improving the speed of cobots, but also there you need new technologies. And so you see that there is capabilities and requirements, and still there is a research gap. And that is, of course, an opportunity to do research, but also to do exploitation. And you have the famous Gartner hype cycle. It starts with an innovation trigger, a new technology, and then you go to a peak of inflated expectations, and then there is a delusion, it doesn't work, and then gradually it goes to the slope of enlightenment and the plateau of productivity. And so Gartner placed robots on the top here, on inflated expectations. I think it's not completely the case, because in the plateau of productivity you have already quite some advanced robots milking cows, surgical systems, like I said before, also in the industry. And for example, my vacuum cleaning robot became much more smarter. Even now with all the toys and the rubbish of the children of ourselves, it still be able to navigate and return and clean and so on, with a quite cheap device. And then on the slope of enlightenment, I think this is niche robots that can do only one thing. And then you have robots that I think go more to unstructured environments, like drones for transport of things, education robots, exoskeletons for rehabilitation, also warehouse robots, which gradually start to be implemented more and more. And in the disillusion valley, there I think also the autonomous vehicles are placed. When you see the predictions 10, 15 years ago, we would all drive with self-driving cars. Of course, there are huge advancements there, but I couldn't yet sleep in my car, of course. But also exoskeletons, cobots, quadrupeds, I think we still need to see the true value of them in our economy and society. And now more and more you have the humanoid robots. There are incredible investments in them. Hundreds of thousands of millions are now pouring in it because they see it after text, speech, images, videos. It's probably physical AI. And so that's really where a lot of investments are made. But I think it's really on the peak of inflated expectations. So what are the core technologies in such a humanoid? So here you see, of course, end-to-end software which needs to run on chips. So yeah, what are there? The foundation models, the chiplets, because I think that we need new processing to make low latency, low power processing. For sensors and chips, 3D touch, I will speak about a bit of Melexis, situational awareness, those communication, like the previous speaker, but also servo motors, a big part of the value of it, the battery system, the body materials, and precision reducers, inertial measurements, and so on. But of course, in order to produce that, you need very large multidisciplinary teams in order to develop that. And so that's why we developed at the VUB Robotics, which is a combination of different labs, like the AI lab, but also the electronics and informatics, and our robotics research group. But because Emmanuel already explained that the combination with the human, that's why we also introduced the human, social, and medical sciences in it. And this umbrella of different research groups, where we've said before mostly worked on human-centered robots, but now we expanded to sustainable robotics, are closely working together in different teams. Moreover, we are also affiliated with Vlaanders Make, which is an institute for helping the Flemish manufacturing industry. I was part of Vlaanders Make till a while ago. Now it's a colleague of our lab, Ixelles, and I joined IMEC. Why? Because, of course, they're the chip research lab of the world, and I see a lot of opportunities that those developments also will end up in robots and have markets there. That's why also the focus on core robotic technologies. And so I mentioned that we are going to startups, and one of the startups that already exist for a few years was even founded with someone from the AI lab, makes bionic prosthesis, and there we started with the focus how we can improve actuation technologies, because typically motors for robots are very rigid, very stiff, and how we can go beyond it and include also the flexibility of the human body to store and release energy in springs, and how we can bring that for example, bionic prosthesis. And so this is the company Ixelles Bionics, who has the IP on the ankle, on the bionic foot. Others in the lab are also working on the knee prosthesis. And here, for example, we participate in Cybathlon, which is an kind of Olympic Games for persons with a disability, but helped with technology. And now we're also trying to transfer the IP of the knee towards Ixelles Bionics. And so also here it's a development of hardware innovations, control of it, model-based control, but a lot we cannot model, and therefore also AI is, of course, important. Instead of replacing human limbs, we also try to augment human limbs, and that are the so-called also wearable robots, in this case exoskeletons, which are categorized in two main families. So on one side, you have the very passive devices. So it are basically springs that store energy to pick up something, and that energy is released back again in the human body to support it. But of course, if you want to do other motions, they often hinder that motion. So they're not very versatile. And on the other hand, you have the powered exoskeletons, where you have batteries and motors and controllers, which of course add weight to the human body. But of course, they're also not very bulky and not very effective. And that's why, similar as the prosthesis, we try to combine passive behavior, storing energy in springs, and active motors where they're needed to make much more lightweight but also versatile devices. And here you see, for example, such exoskeletons for the upper arms. You have to paint the ceiling of your room, how painful it is. But a lot of workers have to work, for example, under cars and so on, but also to lift heavier objects. And also here we want to try to make a spin-off company out of it, which is called Husk. But it's hardware, and hardware is hard. It's, of course, much longer time to market than software. But on the other hand, there is IP involved, which of course has also value. And that is, of course, challenging. Hey, we need quite some investment money to bring this to the market. So hopefully in a few years we can realize this. Of course, in order to test our devices, we need labs to do that. And that's and what also understand what is the impact on the human body with human physiologists, but also even what's the social acceptance of those exoskeletons, and that's also the reason why we work together with the sociologists of it. And so we have about a €1 million lab supported by Flanders Make with motion capture systems like a Viking, but also wearables, insoles, force plates, and so on, so we can investigate objectively what is the impact of different exoskeletons, but also cobots, as you see here, on the human body. So in the drivetrain, we investigated a lot locking mechanisms, springs, and so on, but also the gearbox is an important component, and Pablo is in the room who leads this venturing effort in order to make exoskeleton. But let's hear to the video.
And this is the pinnacle of what robotics engineers can build today. What's the problem? Today's robots require big and heavy gearboxes and motors to move around. This is known as the hardware problem of modern robotics. How can we make motors smaller? One way is to put more teeth in the gearbox to increase its gear ratio. However, this makes the gearbox clunkier. On the flip side, if we try to shrink the gearbox instead, we just end up with a huge and heavy motor again. At Ixelles, we've re-engineered a gearbox with a uniquely efficient planetary movement. Thanks to its novel topology, our gearbox produces higher gear ratios without any need for extra teeth or extra bulk. Our patented technology also minimizes relative movements inside the gearbox, making it more efficient and even lighter. The Ixelles gearbox cuts the weight of the motor gearbox duo by 30%, ultimately making the robot up to 50% lighter. The result is an effective and easy-to-control robot that's eco-friendly and truly beneficial. Ixelles, shifting robotics into higher gear.
So apart from actuation, we also need to improve sensing. And because for our exoskeletons, we need to know the intention to move. Because if I want to lift to stable, which is far too heavy, measuring only the positions, it will not be able to move. And so that's why I need to go to the origin of that motion, which is my brain activity, but that's very difficult to measure. And then, of course, it's looking how the muscles behave. And that's why we have here a centralized interface with EMG, but it is a very noisy data that comes early, and that we combine with pressure sensing, which is cleaner but comes a bit later. And like that we can, like here, detect the intention to move, because if we want to go to a rehabilitation device like here, with a cobot, just moving the arm around, the patient will not rehabilitate. So we need to see what is the intention of the user to move, and then we can assist with the precise impedance control, extra energy in the system in order to move. So this was a finalist for the KOKA Innovation Award, and we wanted to create a company out of it. But first of all, the medical robot is still very expensive. The reimbursement of physiotherapists is challenging in Belgium. And it's a long time to market because it's a medical device. It needs all the certification, and investors are not so willing to take that risks. And that's why the company pivoted to sports injury detection. So that's why it's kind of sensorized sports garments So from the field, we can track not only the motions, but also the muscle activities. And the idea is to go to elite sporters because they have a medical team around them, which can also help interpret the data so that we can gradually also go to recreational sporters, which of course don't have a medical team around it. And so this company has been founded since a few months. Then also we work together with Ixelles. It's a Belgian company that makes very interesting sensors for a lot of cars around us. But of course they also see those new markets of robots. And robots need to go in physical interaction with the environment. And a lot of AI is on vision. But our biggest organ is our skin. And our skin is super important to interact with the physical world. And so in the sensorized interface, they were at only pressure sensors, so not able to measure the shear forces. And so here you have a magnet on top of a chip in an elastomer, and if you put pressure in the 3 directions, this magnet will slightly move, which can be detected, and we can derive the forces in the 3 axes to it. So that's why you see with very small force, even with a paper, we can move this exoskeleton around. And that allows us to measure forces, which are even like torques, which with traditional pressure sensors you will not be able to measure. And we also want, when I want to hold fragile objects, for example this one, I want just enough pressure that it doesn't slide down, but also that I don't press it together, like for example with fruits that would create damage. And here you see that we're pressing on a building, on a block, and you see the forces being changed. And so there we also are experimenting with reinforcement learning to see how much pressure we exactly need to lift up objects. And I think such information is fundamental also for foundation models, and that we not only train on vision, but also on touch interactions. So when I see something and I grasp it, that I can react to this. So we were part of a European project to improve ergonomics of workers with exoskeletons and cobots. And one of the implementations we did was with Volkswagen, where there is this 14 kilo compressor component. Imagine a worker the whole day taking 14 kilograms, so very bad for their back. And so also in industry you have the case that all products have small variations. And that's why we also have a screen on top of it that informs the worker which operations, which task he or she has to do. So it was a nice, successful demonstration, but it didn't end up in the production chain. Why? You see here in the beginning, the robot moves extremely slow. So it cannot reach the takt time in the production facility. So 2/3 of the robot developments, they fail due to speed. Of course, you can say, okay, let's move much faster, but it's dangerous because a human can be there. And that's why we're also making a new venturing effort with Constantine leading it, where we have a multimodal perception pod at the end effector, creating an occupancy map around it, where we want to go close by to cube centimeter resolution. We also combine different sensor modalities that even in different environmental conditions like fog, rain, and so on, we can see through it. And then we also have a digital twin, and you see when there is nobody around, the robot can move at full speed. It's not yet certified, so we were not allowed to go full speed at this fair. But you see when someone comes closer, the robot slows down and then finally stops. And so latency, like Jan mentioned, is super important, and that's why we're also now working together. Like, of course, this is one agent having a perceptor ring, and we cannot share our eyes there, but robots with a communication system can potentially do that. So how we can combine the occupancy maps of different agents, and then, of course, bandwidth, latency are super important. So that's what we're trying to do together under this BrIAS part. And then, of course, when robots need to work together, we also need to know where it is, and that was also the motivation for my last question to Giang. Indoor you don't have GPS position, so how you can know where the robot is? And then you can use SLAM as synchronized localization and mapping. But in many environments, the number of features is not enough to have a reliable position. And that's why we're working, in this case, with ultra-wideband localization. So where the agent only with an ultra-wide anchor on the robot and on the place where it has to go, it knows where to go, and then it uses its slider to do obstacle avoidance and so on. And so that's why maybe in the future we can combine communication with this technology in order to know where is the relative pose of the different agents in the environment. Another aspect is battery management. During Corona, my laptop died because it was always fully charged. So now I have a program on my computer that limits the maximum charging rate, because anyway I don't need it. Maybe when I go to the United States, I want to work on the plane the 8 hours, and then I need the fully charged batteries. On the other hand, on the rest, yeah, the battery just degrades when you fully charge it. And that's why we're also working on a spin-off company, hopefully, that can monitor, because the system knows which are the different paths that the robot needs to take, how we can optimize the charging so that there is a longer lifetime of the batteries. Another aspect is the materials of the robot. Our robots are very complex, and when broken, it's very lengthy repairs, or you throw it away, which adds to the increasing e-pile. And so we use also more and more soft materials. If, for example, this is a very simple gripper, which is a balloon, and you make it stiff by creating vacuum, and then you can pick up objects. But same like the human body, we are not over-dimensioned. We have not very strong materials, but when we are injured, we can often repair our wounds and fractures, and we thought maybe we can also bring that in materials development, and that's why we started working together with the materials, the polymer department of the VUB, to create self-healing materials. So here we exaggerated with a cactus that will of course damage our material, and then you have leaks, so it doesn't work anymore. And then we can apply heat so that you see that the network starts to repair, and the mechanical properties of the material after damage are exactly the same as before damage, which means you can go back to using the system. And so we need to innovate the complete value chain. So we have a portfolio of materials which can be stiff and rigid. We can mold it and print it, which is exceptional because it's a network polymer. Like a tire, you cannot print again, or you cannot even recycle it, because that network is fixed. We can, with the conductive self-healing materials, also embed sensors in it and also have a heating network in it. But we also innovated materials so that they can heal at room temperature. So here we cut the material, and a few seconds later it's healed enough to go back into action. But of course we don't have control of in which environment it's healed. So if it's dirty, then you have the problem that in the car there is the particles, and that's why we also developed heating elements in the soft robot that you can, for example, clean it, you send a current through it, it's up, and it can heal. Moreover, we also made multi-material parts, because if you look to our human hands, we have stiff materials like rigid materials like nails and bones, but also more elastic, and they're perfectly combined. But if we combine different materials, we need to screw them together or glue them together, and often there are the stresses. Where are the failures? But we heal them together so the interface is perfect. And so we have 7 patents on it. And also recently we created a spin-off company, Valence Technologies, as a platform technology, which is sustainable materials, because when damaged it can heal. Moreover, you can chemically and mechanically recycle it. We're using biosources, and we're studying biodegradation. Moreover, we also made a new innovation that we have self-closing suction cups. So when not all suction cups are in contact with an object, you cannot create enough vacuum and you cannot pick it up. But our suction cups, due to the design, closes itself, and so you can pick up a more wide variety of objects. So how you create technology that goes from very low TRL level to valorization. Yeah, for that you have the technology readiness level. 0 or 1 is an ID, and that's where we have our very fundamental projects like ERC grants, or also for the self-healing we had a FET Open, which is now called EC Pathfinder, which is blue sky research. But then you end up with TRL 3, nice lab demonstrators, nice papers, but then the valley of death happens, because for an investor, it's still too risky, and for the research part, yeah, most of the innovations are done. And then we were very lucky to have an AC transition, where the ideas do on one side do the business aspects, and on the other hand, maturing the technology. And so that's how we can overcome this valley of death towards a spin-off creation. So now we're applying for an AC accelerator grant for the spin-off. And of course, it's a platform technology, so you can go to much more markets. And so that's why we're developing parallel projects to go to new markets. For example, we're studying self-healing medical phantoms to do surgical training. And how we do an IP management, yeah, it's also, I think, a challenging thing. So of course, for spin-offs, often they need patents, because that's, of course, something of value for the investors. Some things you also need to keep secret, because, yeah, all the processing parameters are, yeah, difficult to patent, but throwing them on the street is also not so interesting. But on the other hand, those technologies need to be used in applications which are beyond the capabilities of our lab. So that's why we also make tutorials, open source control, where we, for example, had a tutorial paper, how to use our materials, so that it can go beyond applications, beyond our capabilities. I think it's also very important to do VOCs, voice of the customers. In the beginning, we develop our technology, and then we think, maybe it's nice to make a spin-off company. But the needs of we as researchers want to add more and more complexity and cool things, but that's not what the market needs. Because they need cheap products, robust products, and so on. And so instead of doing the VOCs at the very end, when basically your money is burned, your research money, we try now to do it much earlier in the process. So for example, SafeBot, the researcher, is doing a lot of voice of customers with a lot of companies to understand their problems, with their needs, in order to develop a product target on those needs. I think it's also important to don't try to conquer at once the world. What you see now, the markets for humanoids are billions of euros, and you think, wow, I will enter it. But of course, they are the big sharks. And so I think it's better to go to a beachhead market. The idea comes from the World War II. First, you land on a quite safe beach with not a lot of competitors, and then you gradually take different parts of the market. Now we are developing all those different startups. We thought, yeah, why not combine them in a kind of accelerator hub? Because if you see other countries, they have much more startups. Of course, you can say Denmark, Germany, United Kingdom, that are much bigger countries. Of course, they have more robotics companies. But if you see Denmark, Switzerland, the Netherlands, and we compare the number of robot companies divided by million of inhabitants, we see Belgium is behind. And that's why if you have an ecosystem, you create that, innovations can accelerate. You share talent. Maybe one company goes bankrupt, but that person has a lot of talent, so can you not reuse it, or has a different role in the company? Also even reinvest money. And that is what we exactly want to do in the robotic startup in Zellik, where VUB has a research park, where there is also the new VUB supercomputer hosted. It's a park on sustainability. And so we want to offer different activities to the companies, both office space, but also supporting them in research, but also infrastructure, because again, robots is a hardware-intensive component, and will all the companies have CNC machines and 3D printers, which is a lot of capital that you need to invest in it. Why not just share those facilities? Also, coaching, networking, upscaling, funding, and so that's why we're now collecting a lot of companies to offer services to them, so that we can make those robotics companies as successful as needed. So thank you. So that was robotics, how we go from core robotic technologies, from very basic innovations, to gradually increase the TRL to support existing companies, but also create our startups. Thank you. Are there questions? There mics being...
Oh, okay, so are there questions? So if not, I have one that is, of course, the creation of a startup or a spin-off. It's something that involves multiple actors. One actor is the researcher that takes the risk,
which is super important.
One other aspect is the laboratory, but also there are a series of other actors, like the university itself, that is at the end the owner of everything that is IP and so on, possible investors and so forth. What do you think that is crucial in terms of policy to foster the creation of spin-offs?
Yes, so for a company, indeed, all the IP developed is owned by the university, but of course the spin-offs need those IP, and then you need an agreement between those two parties. And yet the entrepreneurial team in it is super important, because they need to turn from a researcher or an excellent researcher into an excellent entrepreneur, which is different capabilities needed. So it's a whole learning process. And then, of course, they need to go in negotiation with the university. And there we see that, there is still some friction currently. And that's why we think that maybe a kind of framework is best in place. And that, for example, in the Netherlands, the different universities with the different stakeholders agreed on such kind of framework guidelines about IP rights, royalties, shares, and so on. And I think this is a bit missing in the Flemish landscape, and I hope that can be realized, because, of course, as an entrepreneur researcher, you're between the investors that say, don't pay for it, maybe even do it alone, and the university that, of course, also invested in it, in the patents, and also the research group, where you need to have a fair deal, I think, because on the one hand, you need to make that a spin-off company is viable. If you take too much money, it will die, so it's not in the interest of the university, because then your patents are worth nothing, or you need to resell it, which is even sometimes very challenging. And so having, of course, a fair thing. And so I think this needs to be improved. I think, on the other hand, because now we have several startup initiatives, it inspires also our researchers. And that's why I think it's also very important that they kind of unite to share experience, best practices, stupid mistakes they did, because you can also learn a lot from that. And it's often now all the successes, but you don't see all the failures behind it. And so that's why it's very important, I think, to create such a hub of robotics companies, where we also want to attract from other countries or from Belgium companies to it, to really work together with the specific needs of hardware robotics companies.
Thank you. There's a question there.
Yeah, so I was wondering... Hello. I was wondering, so as a research group, you've created many successful startups. What are the most contributing factors to create such an ecosystem? Is it to make your young researchers enthusiastic from the beginning? Is it to make sure you understand the market very well and choose the right research topics? What would you say were the most important actions you took as a research group?
Yeah, of course, first of all, we don't have so many successful startups yet. They're in development. But I hope they're successful ideas at the moment. But I think it's, also as a research group, we had to learn a lot. I remember our first startup idea was a social robot, because we did also a lot on social robots, and we thought to make it open source, because we thought Arduino and open source printers, it works pretty well, but investors are not very keen on that, so that I think was the first realization. We really need the patents, and more than patents, also the IP. Then I think another aspect was doing much earlier what investors need or want, because they also do their homework, and do it as early as possible, because then you still have the funds. Of course, you also need, and nobody asked at a certain moment the iPhone or maybe the car if they had horses. The traditional thing, you want a faster horse. And so you also need to push there with your own vision. So that combination for innovation and persistence, because it took us also a while to transfer to investors the idea of, for example, the SafeVod concept. And so, I think then it's also a bit of part of luck to really find kind of a value chain of who wants to invest to buy your product. And I think it's very important to try quite early on to find your first potential customer who is willing to pay even a very small amount, because then he has to go in his or her money pocket to do it, because otherwise, cool idea, continue, and when it's there, I will wait. So I think that's also an important aspect, and and that's a bit what you create open and what you do protected, and to play a bit, to have a balance there, especially because it's not an end-user product sometimes, it's a component that needs to be implemented in a bigger system. And so, so I think our next step is, creating that robotics hub to really share experience and networking and, learn from each other, and also offer services between each other. And for example, our centralized interfaces is maybe important for the exoskeletons, for example, and attract other companies that fit in the value chain.
Thank you, Bram, for the super interesting talk. Could you share with us your maybe experience or observation about the interest of the investor currently, the landscape of the funding from investor currently compared to maybe 5 or 6 years ago, so before and after COVID?
I think it's challenging because we don't have so much VCs, we don't have so much risk investors. If I see the difference with US and Asia, where even a while ago I saw companies that I thought, do they bring this to the market? I think there could be much better products, but on the other hand, they had a company, they had interactions with customers, they learned probably very quickly, and probably several died in the meantime, but on the other hand, several were successful. It's like in electric cars, Tesla laughed with build your dream, buy it. In the meantime, it's a very successful company, I think. And so I think it's a bit a problem, a challenge in Europe, that risk investors don't want to take so much risk. They want a very short time to market. They also want to see that you have different options, which I don't think is good. I think you need to go for one market, and if it's needed, pivot very fast. And so we don't have a lot of competition in it, so we cannot put different risk investors against each other to have the best deal of it. And so I think in Europe the research is very good. Europe invests quite a lot in it. So I find it very sad where are the humanoid companies developed. I mean, Europe has very cool humanoid robots from DLR, Karlsruhe, IIT, and so on and so on. and where are the companies in the US and in Asia. So I think we really need to work together to make a robotics thing, because I think on a geopolitical level, that will be otherwise challenging.
There is a question there.
Yeah, it's a little bit continuing. Thanks a lot for the talk. It was really insightful and nice to hear. Continuing on this topic, you said that Europe really needs more investment in robotic startup, but isn't there a problem of just quantity, which is the capital is mainly in the US? And a lot of European companies do try to deal with that by opening an office in the US or opening a branch in the US. Is this something you're considering, or is this something that is part of your thinking, or is it something you would rather avoid?
Yeah, I think now the situation in the US is not so interesting anymore. I even see a bit the opposite effect that, American companies are, I think, more and more interested in Europe. I think you also see it in the stock market, how it goes down, and in Europe it goes up. So it's maybe an advantage, although I find it pity for the US. That we see also, so we didn't go abroad yet, so that's why I also see a role for the robotics hub to make connections with other robotics hub, like Pittsburgh and Silicon Valley, so we can exchange companies a bit to say, and also have a network of networks to say. It's also very challenging, and we don't only need to look to US, but also I think to Asia and especially China, where also aspects on IP are not so trivial. Again, also there it's a challenging thing, and that's why I also think we need to combine this hardware and this AI software, because on the hardware you can take the IP. You see open AI and then DeepSeek and Chevrops go down, because where is the IP there? But I think you need to enable the hardware with AI, and that combination I think needs to be, will be important, and that's why I feel a bit with Europe that they now put a lot of effort and focus on generative AI things. I'm very afraid that they will forget that they're also very strong in Europe in hardware, and that they will lose these things, and that we will develop a lot where others will copy and use it. So I think, we need to keep that combination. And again, Europe is quite strong in manufacturing, in hardware, but with the recent trends, I feel that we're losing that aspect, and that it's, I think will be a crucial mistake, I think.
Do you know what's the percentage of research making by the company themselves in R&D, and what's the most important in Europe? Are the company that they're doing their own research to provide some new tools, or the universities, and what's how they can mix, and what's the percentage of each part?
That's for me hard to say. I think the role of universities is a low TRL, the basic innovations, and I think it also, underestimated the importance of open source software and AI, where a lot of companies run on and can make very fast software because a lot of code is openly available and they assemble it into systems. And for example, all the underlying technologies of your iPhone, if you see the talk of Mazzucato, I think she's an Italian economist, all the basic technologies from lithium-ion batteries, GPS, multi-touch screens and on are all funded by government-funded projects. So I think the importance of the government is the biggest risk investor at the moment. But of course, creating a company and making something so beautiful to say as an iPhone or a Samsung phone and so on, that's the role of the companies. And so, that interplay between government and companies are important, but that also means that those companies need to pay taxes, because we need to raise engineers, we need to raise our students, and also to pay for the innovations that then gradually go to industry, but it takes a very long time. It's very risky. I mean, all the developments I show, that is often 10 years of research in quite large teams. So and with a lot of a graveyard of research that also failed. And so the lower the TRL, the higher the risk, but then also the society and the government and the population has to accept that there are risks and then gradually to go to innovation. But how much companies do, it's challenging to say. Also to say that often it's complete secrecy. So Dyson has 700 engineers in robotics. Nobody knows what they're doing. We would probably have a guess. It's probably household robots. You see, there are also the vacuum cleaners, but I think they're preparing much bigger things.
Hello, Bram. Thank you. Did you ever consider a subject in the educational or entertainment field?
Maybe social robots falls under it, but not in fact yet. But for example, Disney has also quite a big research lab on robotics. And for example, I just heard that one of their cool social robots is entering the Disney, how you call it? Disneyland in Paris. So also robots are used for entertainment. But we didn't go into this, except more educational robots for children with autism and diabetes. But because of the declining interest of Europe in it, we had to abandon that.
So I will go for my privilege for a last one, because otherwise we'll stay a lot. And it's more a general question that is about the role of university in all of this, because as you were saying, university has already a very complex task that is education on the one hand and research, but not innovation, in the sense research and low TRL innovation. So one thing that I was always thinking, and somehow you also gave an answer during your talk, is if university is the best place for the management of a launching of spin-off, or we would need more of some intermediate layer between the research and then the industry.
So I think we really need to reinforce entrepreneurship at universities, but also understand it's a very challenging field. It's also a matter of continuous funding, and typically a project is 3 years, and then that's my daily work to write endless amount of projects in order to continue to fund it. And also not only it's maybe one of the slides that should have shown, but for example the research team on the cell feeling was from both the material side as the robotics side is 20 people. Even one European project cannot pay for that. So it's really a combination of a lot of grants on national level, FAO and European grants and so on. And also when even a big project finishes, after 3 years, they're all on the street, and how you can maintain that, or at least the core of that team, in order to go to a spin-off. And that's an incredible big challenge where often, also like the social robots, it just failed and we couldn't go to the next step. Probably we were also not yet ready for that. But it's quite some effort to find the funds in order to continue those developments, to go to companies. And that's the thing. Does the government need to pay that, or do the risk investors have to pay that? I mean, that's a bit a balance that society has to take.
Also because anyway there is a gap. There are certain TRL for which there is not the effect, wow, you have just to keep tuning,
for example, on the self-healing materials, we had a science robotics paper, and it was super cool, and now it's fine-tuning the materials so it's all the quality standards for a long time, which is not so super cool anymore and hardly to publish, but it's critical. Also affordability, I think it's also a very quick question. For example, that I like of the Melexis sensors, it's not a sensor of a few €1,000, but how to design it so it's cheap, because you need many of them, and you don't want a humanoid of millions of euros, you want, or hundred thousands of euros, you want it in a cheap car. So that means all the basic components, need to be cheap and super reliable. And yeah, that's also a very important but challenging part, and that's also risky for investors.
So I think that there will be many other discussions going on, so I would like to thank again Bram.
Thank you.
And to thank him especially because he could have been probably much more in his comfort zone presenting us his latest result from the scientific viewpoint, while instead he brought something that touches many of us as academics and for which we are very sensitive and very often also very discouraged, I must say. So thank you, Bram, again, and thanks to all of you. I imagine that finish this formal part, we will have various discussions. There will still be a coffee. And thank you for being with us.
Thank you.